Thanks everyone for coming out. I'm hoping I don't get a pie in the face or something at some point. We'll hope this works out. So what I want to do is I want to talk about a project I've been working on for the last really 6 or 7 years called model thinking. And the idea here is to think about how we use models to confront what is really an increasingly complex social world. So what I want to do today is I want to sort of give a broad overview of that project, talk about sort of theoretically what we're trying to accomplish, and also talk about sort of the difference between how social scientists use models and how physicists use models. And the sort of takeaway from this at the end, I think, will hopefully help you be better thinkers in terms of just how you might, when you confront this complexity, think about using multiple lenses as opposed to a single lens. Just a quick bit of background in terms of how this is going to go. My style is to speak somewhat slow and then sometimes really fast, but to use lots of slides. So there's 167 slides, which is 18 seconds per slide or something like that. So it's going to feel a little bit like I've duct taped your hands to the back of a car and I'm driving you off. So here we go. So I'm going to start by talking about why we model. What are the reasons why we model? Then I'm going to talk a little bit about how physics differs from social science. Then I'll get in very briefly to complexity, and then I'll get to the meat of the talk, which is this idea of one to many, many to one. Here's the idea. In order to make sense of a complex world, we need many models. We can't have a single model. So the idea is going to be many to one. But we can't really do many to one if every time we confront a situation, we've got to construct a whole new set of many models. So the sort of jujitsu around that is going to be to have, for each model we use, figure out ways to apply it to many situations. So one to many, and then given any one problem, we can apply many models to it. And then at the end, I'll talk about this idea that what we should be is what Isaiah Berlin called foxes, people who have lots of models, and why being a fox is better than being a hedgehog, which is someone who has a single model. So someone who tells you how the world works, I'll tell you at the end, is actually worse than random, right? So you'd rather be a fox than a hedgehog. Okay, so why do we model? This is an era of what we call big data, and there's people who say we don't need models anymore, but that's just not true, right? We need models for lots of reasons. So why do we model? Well, one reason we model is just to get the logic right, okay? So mathematical models are a lot better than metaphors. So we have metaphors that say, dig the well before you're thirsty. But the problem with any metaphor, any proverb, is there's an opposite proverb. So we could say, dig the well before you're thirsty. We could also say, don't cross the bridge until you come to it. These point in opposite directions. The reason we have models is to understand the conditionality of that logic. So James Haldane, the famous biologist, once wrote that, suppose you drop something down a 1,000-foot mine shaft, what works? One model is just the standard sort of gravitational constant model, right? The other model is a terminal velocity model. If you drop a rat, or if you drop a mouse down 1,000 feet, you should use the terminal velocity model. It'll just walk away. If you drop a horse down a 1,000-foot mine shaft, it'll go splat, right? And that's because you want to use the standard gravitational model. So you want to understand the conditionality of the models you use. This is my colleague Charlie Doring. Another reason you use models is to try and explain. So Charlie studies turbulence. When you think about turbulent systems, they're incredibly complex, and what we need simple models to sort of unpack why we get these things like turbulent flows. We also use models to predict. So this is my colleague Melissa Eisenberg, and Marissa does stuff on sort of cholera and how cholera relates to rainfall. So what she does in her work is she writes these sort of wonderful graphs and shows how rates of cholera can be predicted based on rainfall in previous periods, okay? We also use models to take actions. So this is Timothy Geithner, who was head of the New York Fed at the time, and 2008, as you probably all remember, things didn't look so good, and there's a question of which banks do we bail out? Now you could think, well, we should probably bail out the banks that are the biggest. We should bail out the financial institutions that have the most resources. But instead what they did is they used these sort of models, and this is a model of each one of the banks, and the thicker the line, the more that bank or institution is connected to other financial institutions. So AIG has these huge thick lines, which basically means if it coughs, everybody else gets a cold, right? Lehman Brothers, which you see to the far left, just has these light gray thin lines only to a couple places, which means if Lehman Brothers dies, Lehman Brothers dies, right? So what happened was when Geithner has to make the decision about who he bails out, he doesn't make it based on some sort of just balance sheet appraisal. He makes it based on a series of models, this is just one of them, that tell him what's likely to happen if I take a certain action. So we do policy with models. We also try and design things with models. So this is Jenna Bednar, one of my colleagues in political science, also my wife. And she does work on how do you design robust federal institutions, right? So one of the things that's happening is there's sort of a general trend towards democracy, but also some of these democracies take place in countries that are very diverse, and so federalism is a very natural way to think about it. But how do you construct a federalism, and how should the federalism depend on the particular country in which you're embedding it? And so one of the things we do to try and construct those federalisms or federations is to construct models. Okay. So in social science and in ecology, we often have a whole bunch of models we throw at a problem. Now this is different. This is Saturday morning physics, so I have to have a slide that says physics, right? Otherwise I don't get paid. There's a famous paper in philosophy of physics, of which there aren't that many famous papers, called The Unreasonable Effectiveness of Mathematics in the Natural Sciences. And Eugene Wigner, who's at Princeton, he goes on and on about like, we're good. You know, let's just talk about how freakishly good we are, right? And like, you know, when they found the boson, it wasn't like they were within 2 standard deviations. It's like, 10 standard deviations. It's just, they're way better than social scientists, right? At pretty much everything. So why is that? And not only are they way better, they often just have like one model, like force equals mass times acceleration, right? It's just a single model, and it works unbelievably well. And they're incredibly confident about their models. Like, I like some of my models. This is Boltzmann. He puts his model on his gravestone. Right? No way. So, like, Jenna had that federalism thing. That's probably not going. It's going to probably say, to my loving husband. It's not going to say, here's how you construct a federation. Because the thing is, the social world is constantly changing, right? So this talk might be called sort of the reasonable ineffectiveness of mathematics and social science. Right? Because we're just not as good, okay? Why? Why aren't we as good? The first thing is the diversity of the parts. So a lot of my work is on diversity. Here's a copper atom, right? And then here's another one. They pretty much look the same, right? Here's Fred Adams, right? Here's another Fred Adams who plays trumpet. They don't look at all the same, right? So the thing is, 2 copper atoms are identical, but pick any 2 Fred Adams, you're likely to get anything, right? Second thing is, the parts don't think. So here's the copper atom, and I'll share with you every thought it's having at the moment. Okay, now we're done. We know what it's going to do, right? We can explore carbon atoms. We can look at how many electrons in the outer shell. We know what it's going to bind to, right, if you take a chemistry class, right? So we can figure it out. It doesn't have a model of the world. But if we look at Fred has all sorts of models of the world, right? It's incredibly hard to figure out what Fred's going to do, or what I'm going to do, or what my friend Bill Zimmerman in the back is going to do, because people are sophisticated. Third thing is large numbers, and this is where the physicists really have it over the social scientists. If you take a cubic inch of water, this is how many water molecules are in it. So in statistics, we like to say that you need 20. You need an N of 20 to be able to do statistics. Okay, that's a lot bigger than 20, right? So when you've got 600 whatevers there, right, it's just going to work. The averaging is going to work out. And that's why Boltzmann can be so darn confident that he can put this on his gravestone, right? If we look at social systems, like the biggest number we may get is something like 435, but these are incredibly diverse people in the House of Representatives, and we don't know what they're going to do, and they have all sorts of weird models of how the world's going to work, and so therefore they're very hard to predict, okay? So what happens then, and this is sort of why I spend the time I spend in the place I spend it, in the Complex Systems Center, is that social systems are just more complex. Now, if you go to a restaurant, there's a very good chance your salad dressing will be complex, right? Or the salmon, and your wine is almost certainly going to be complex, right? So what do we mean by complexity? What we mean by complexity is we turn to the physicists. And so Steve Wolfram has this wonderful book where he talks about, so a system can really sort of be in 4 different states, right? So in the top, it can just go to an equilibrium. So you want to think of time sort of moving vertically here, from the top to the bottom. So something can just become sort of all black, all dead. In the upper right, you can think of something alternating. So something can be in equilibrium, or something can alternate. The third thing, which is in the lower left, something can be completely random, right? So you can get sort of, you can imagine systems that are stable. Like if I just set this pointer down, it's stable. I can think of things alternate or periodic, like the planets revolving around the sun. And I can think of just complete randomness, like middle school, something like that. And then class 4 which is the space where we're trying to figure things out, is what we call complex spaces, right? So in the bottom right, where there's patterns, but those patterns sort of change over time and evolve, and it's sort of tricky to figure out. So you can sort of black box things and say, look, there's just something going on, and what comes out of that isn't periodic, isn't stable, isn't random. There's some structure to it, and we could use Fourier analysis or wavelet transforms to find different waves at different lengths and stuff like that. But the way we think about this is there's really sort of two broad classes of definitions that refine Wolfram's idea. The first one is what we call Bohr, which is between ordered and random. So if you do statistical analysis, you could say something's ordered, you could say something's random. If it's kind of in between, we think of that as complex. Or another way, there's a whole class of definitions which I call deep, which are difficult to engineer, evolve, or predict, right? So if you look at the human eye or the human brain, you think that probably wasn't evolved just due to one genetic flip. It probably took a long time, and so that would make it complex. If you look at a car, you'd say that took a long time to engineer, so that's complex. If you think of something that you're trying to predict, that's like the stock market, which is very hard to predict, that's also going to be complex. Okay, so here's unemployment rates in the United States. If you look at that, that's sort of between ordered and random, right? It's also going to be difficult to explain, and it's going to be difficult to predict. Now, the interesting thing about human systems is parts of them are complex and parts of them are not complex. So if you look at oil production, which is the black line here, that's actually fairly easy to predict. It goes up, right? As the world economy grows, as world population grows, the amount of oil we need to support society increases. You see a dip, that dip is World War II, right? So there's a dip, right, and then things go back up. If you look at oil prices, those are complex. Why? Well, because the process that drives oil prices are a whole bunch of people who have models. People can store things, people cannot store things, right? There's strategic play between countries, right? Putin, the Middle East, everybody else is having all sorts of fun creating these giant things that go up and down. That's complex. So within any one system, you're going to see some dimensions that are in equilibrium, some dimensions that have patterns, and some dimensions that are complex. And what we want to do is we want to use models to try and make sense of this. Well, here's the problem. Our models have to be simple. So this is Picasso's model of a bull, right? The models have to be incredibly, incredibly simple, but the world in which we live is really complex. And so this is why we have to have many models, right? Because all models, because of their simplicity, are going to be wrong. They have to be. But Box goes on to say some of them are useful, and that's sort of the point. So the solution we have here is to have lots of models. And there's sort of a naive way to think about this, which is to think of the truth as sort of being at the intersection of all these lies, right? These incorrect models. But if those incorrect models are incorrect in different ways, those differences can in a way cancel out, okay? So what we want to think about then is there's some problem out there. This could be a problem of design. This could be a problem to predict. This could be a problem to try to take an action like Geithner had to do. This could be just to try and explain something. And what we want to do is we want to think about having lots of models that we can put in play to sort of accomplish that, okay? Now again, the problem though, right, is that we can't construct lots of models for each case. So what I want to think about is how we can take one model and apply it to many cases. So what I want to do is I want to start with sort of the simplest thing I can think of, which is the model of a cube. And I want to show you that if you actually have some fun with the model of a cube, you can apply it to lots of problems. So this is the idea of one to many. So here's the really complicated math part, right? Area equals length times width. Volume is length times width times depth. Now, I was giving a talk to a group of CEOs one time about models, and someone says, someone jokingly said, can you use this model to make $1 million? And I said, no, in fact, you can't, but you can use it to make several billion dollars, right? In sort of a Dr. Evil sort of way. And the person who did, his name's Stavros Niarchos, who's a Greek shipping magnate, and remember the oil production graph I show you? Pretty much everyone knew the world was going to be rebuilt after World War II and oil production was going to go up, right? There was going to be increased need for oil. And people pretty much also, everyone knew most of oil was in the Middle East, and we also knew that the oil had to go to Europe, America, the Far East, those sort of places. And you have to ship it. Well, what Niarchos knew, that other people knew, because most people, I think, knew this, but what he knew is how to apply this, and so what he said is, look, I've got this really complicated model. He went to some bankers and said, here's my model. And the reason this model is important is if you build a ship, surface area goes up square, because that's the sides. Volume goes up, told you naval architecture. volume goes up cube. So the cost of the ship goes up square. The amount of oil you can take goes up cube. So what you want to do is you want to build the biggest freaking ship you can build, which is what they do, right? How big are these ships? They're like Sears Tower big, right? Now, Niarchos' first ships weren't this big because there was a trade-off. He wanted to build them fairly fast. But if you do some back-of-the-envelope calculations, he was probably making $250,000 per trip. And the ships only cost, like maybe $20 million to make. So each week he was making like $250,000, just based on this simple formula, right? Okay, but let's go back to this. Area, square, volume cubed. And let's think about a mouse and an elephant, okay? So here's a model of a mouse and an elephant. Actually, this isn't a very good model. Here's a better model. Here's a mouse and an elephant. Mice and elephant both have basically the same surface temperature, right? And they both in the same sort of internal temperature, right? If you give them a thermometer, they're going to have this, they're going to be 98.6 like us. The mouse is really small, the elephant's really big, and they're both composed of cells. And you think of these cells, a famous physicist once explained to me, think of these cells like little fires inside them that are sort of like, autocatalytic sets that are creating heat. And that heat has to be dissipated through the surface area. So again, let's use our formula in a really complicated way. The surface area of the mouse is 14 square inches, and the volume is 3 cubic inches. So that's 5 to 1. The surface area of the elephant is 57,000 square inches, but the volume is 864,000 cubic inches. That's 1 to 15. So the difference in ratio here is 75. That would mean that if the elephant had the same size fires inside each of his cells that the mouse did, the elephant would blow up. Right? This would be like totally cool. We'd all stand at the zoo waiting for the elephant to get the sort of critical size. One more bite of hay and that sucker's going to blow, right? It'd be like Old Faithful. The point is, that can't be true, right? Something's got to give. And so it turns out if you do look at the data and you look at the mass, that's on the horizontal axis of different species, and you look at the metabolic rate, which is in some sense how hot those fires are burning inside the elephants, on a log scale, those lie on a line. They have to lie on a line, because if they didn't lie on a line, the elephant would either freeze or blow up, right? So again, an incredibly simple model, square and cube, gives us this sort of profound understanding of why metabolic rates lie, at least on log-log plots, on a straight line. Okay, same model. Many of you probably go to the doctor and they tell you your body mass index, and you say, shouldn't have had the donuts, Saturday morning physics, right? This is weight over height squared, okay? That's what they do. And there's these things. They have the pink region for obese people, the overweight, normal, and then underweight. And your doctor basically tells you, you should be normal weight. Now, if you look across, this is a small data set, I think 600,000 people. If you actually look at mortality as a function of body mass index, what you see is you see the min, which means like most likely to live the longest, is at 26. Now, if I go back, that's actually overweight. So donuts are good, right? So you basically got this thing where you're better off being a little bit overweight. So what the heck is going on, right? So I put this up just because it is Pi Day, right? So we've got this thing that it's good to be overweight. How can that be? Well, body mass index, let's go back to our really complicated formula. It's taking weight over height squared. Okay, so Edwin Everett wrote this famous book called A Square about this planar guy. But like last time I checked, I'm somewhat three-dimensional, right? I'm not a plane. And so maybe because it's doing height squared, it's screwing something up. So here's this guy, Kevin Durant, fatty 2x4, right? That's what we'd say. He's overweight. He's overweight. Because it turns out that this scale is biased against tall people because they're using the squared term. And so what you'd like to do is you actually should be using something like height to the 2.3. But when they came up with the formula, they didn't have calculators, and so they said, let's just use squares. And they sort of baselined it off British people who tend not to be as tall, actually British schoolboys. And so it works really well. BMI works really well if you're 5'7", and it starts working really bad if you get a lot taller. Okay? So as you eat a donut, just stand a little straighter, everything's fine, right? Now, the reason why 26 is the right answer there isn't because you're better off being heavy, it's because actually height correlates with sort of general health in a particular way, right? So if you end up being like 6 feet tall or something, then you probably weren't sickly as a child and growing up. And so that's really capturing the fact that it's just height actually in a weak way correlates with health. Okay. One more. Area square volume cubed. And I want to talk about a book by Sheryl Sandberg called Lean In. And one of the things she talks about in this book is how there's all sorts of subtle discrimination against women in the workplace. And I was at Boeing a while back, and they said, it's interesting. We hire every other year about 20,000 people. And we hire equal numbers of men and women. But at the top of our organization, it's almost all guys. But yet when we look at our organization, we're actually not very biased. There's, in fact, we seem pretty fair. And I said, that's actually not surprising. So we're going to take that square cube thing, and we're going to ramp it up to more dimensions. We're going to have an n-dimensional cube. So let's suppose that it's the case that at Boeing, 60% of people get promoted at each level, if you're a man, and 50% of women get promoted at each level. So there's just this slight advantage to men, ever so tiny. And they start out by hiring 10,000 men and 10,000 women. But to get to the top of Boeing, you need a whole bunch of promotions. So at level 2, there's 6,000 men and 5,000 women. 60% of the men make it, half the women. 3, 4, 5. By level 5, the ratio is now 2 to 1. 6, 7, 8, 9, 10. Now you're in the C-suite, right? You've actually got an office with corners and 2 windows, stuff like that. You got 100 men, 20 women. You go up 2 more levels, you have 36 men and 5 women, which is exactly what most corporations look like. So what's interesting is that you have these 2 facts that don't seem to align. One is you've got mostly men at the top of these corporations. The other thing you have, and Abby Stewart does a lot of work with this big advanced program at Michigan, you see subtle but small biases in most organizations. Turns out a very simple model explains that those things actually perfectly align. Subtle and small biases combined with lots of hurdles result in massive discrimination at the top. Okay? Again, all explained by that simple sort of model. Okay? So that's the idea of sort of one model to many problems. Now let's go the other way. Let's go many models to one problem. Now the thing is, I could do design, I could do understanding, I could do explanation. I'm going to do prediction, because predictions gets more fun. Okay? So we'll talk about prediction. How do we predict? So there's a wonderful book, if you want some good bedtime reading, because it'll actually keep you awake. So there's a book by David Arell called The Future of Everything. And he goes through all the ways we've predicted over time, from moles on the body, animal entrails, right? All that stuff that didn't work very well. Okay? Now, he argues, we use models. Now, there's an outside chance that 20 years from now, someone will be up giving a talk here, and models are going to look just as stupid as neighing of horses. But probably not. Right? They're sort of a categorically different thing. So what I want to do is I want to do this sort of first the undergraduate version and then sort of the graduate version of how collections of models can make better predictions than individual models. So I'm going to start out by framing this in the context of a book written by Jim Surowiecki called The Wisdom of Crowds. How many know this book or have seen this book? Okay, great. Okay, so in this book he talks about what is it that make crowds of people better predicting than individuals. Now there's another group called The Madness of Crowds by Le Bon that was written a long time ago. Le Bon, they basically say the same thing. Le Bon says crowds are mad when everybody thinks the same way, i.e. everybody's using the same model. And Surowiecki says crowds are smart when people think differently, i.e. everybody's using different models. Let's see sort of how it works. So Surowiecki, because he's writing a book, he's trying to sell copies, he begins with an amazing story. So here's the amazing story. 1906, West of England, Fat Stock and Poultry Exhibition, 787 people guessing the weight of a steer. Average guess, 1,198 pounds. Actual weight of the steer, 1,197 pounds. Not bad, right? Now, we could then say, anytime we have to guess the weight of a steer, let's get a crowd. Seems reasonable. Somebody did this at a TED Talk a couple years ago in San Diego, where you think people probably aren't as good at guessing the weight of steers as people in 19th century England. Probably true. They were within 2.5 pounds. So they weren't as good, they were close. So what's going on? Well, here's what's going on. You can actually write something called the diversity prediction theorem. It says crowd error equals average error minus diversity. Now, when I write this, again, I'm a social scientist, and so there's probably some preconceptions. Ohio State this year had this thing on their wrist that all the players wore, like output equals effort plus resilience or something like this, right? The football team wore it. No, this is like real math, okay? This is like Pythagorean theorem stuff. Okay, so this isn't one of those team equals togetherness plus effort plus ambition plus meaning or something, right? Which I have no idea what that stuff does, right? This is a statistical theorem, okay? So what does it say? The crowd error, if you look at this, we're going to unpack it. The crowd error is just the crowd's prediction minus the true value squared. We square these things because This is what we call in statistics the archery theorem. Like if you shoot one high and one low, you can't then say bullseye, right? So you make everything positive. So that's the crowd minus the truth squared. And then we sum up, that sigma thing is a summation sign. We sum up over all the people, their predictions minus the true value, and we square those. So that's just sort of like how big are the errors of the people. And it turns out, here's the really interesting thing, and at some level, like I live in this country where we argue that democracy and markets work. This theorem, in some sense, explains fundamentally why that is sort of true. Because what you might think is that the ability of the crowd, whether that's voted or whether it occurs in a market, is kind of equal to the ability of the people in it. So the crowd error should sort of equal the average error of the people in it. Turns out that is not true. It's better. The crowd's error equals the average error of the people in it minus the diversity of their predictions. So the crowd is what comes out of a market is actually always better than the people in it, on average, unless the people in it all think the exact same way. And so the amount by which it's better is based on how different the predictions are. So if you look at Galton Steer, the crowd was within a pound. The average error was 29.56. These are squared errors, so that's like 57.58 pounds. Okay? So when Jen and I moved, when I was at Caltech, Jen was at USC, we moved to Iowa. There's less to do in Iowa than LA. Slightly less. So we do, like, what's that phrase? When in Rome, right? So we bought cattle when we moved to Iowa. We bought a little farm and bought cattle. And you go to these cattle auctions and they fill you, ironically, given today's date, with a lot of pie. And these cattle come out and you try and guess the weight of these steers. And the thing is, you can guess the weight of these steers within about 56, 57 pounds. This isn't rocket science. These weren't some sort of savants who could like just know the weight of a steer. They were off by like, like what normal people would be off. What's interesting is they also happen to be diverse. And the reason they were diverse is probably some sort of anchoring and adjustment bias. They probably knew the weight of their own steers, right, and adjusted from that. So whatever the cause of the diversity, this is why you get it right. Now, if you take Jim's book, and he and I have done it together with a friend of ours, Michael Mobison, and take all of his examples of wise crowds, they all look exactly like this. The reason why is it's a book about wise crowds. So he's only taking cases where the crowd error is small. It's also filled with amazing stories. If it's an amazing story, it's got to be the case that the average error is big. Because it wouldn't be amazing if the average error were small. And so therefore, if the crowd error has got to be small and the average error has got to be big, that means the diversity has got to be big, which is why he says wise crowds have diversity. Now, let me walk through the logic just very quickly, just because sometimes too much math can be sort of overwhelming. So last year, my family spent the year in France. And Steve Martin famously said, those French, they have a different word for everything. Right? It's absolutely true. And so we would go to the store, we'd go to the market, and it would say things like oofs, but that we could figure out that's probably an egg. And we knew what a euro was, but then there's this other word, which is douzaine, I'm guessing, right? So we don't know what that is. So my son Cooper and I might say, I think it means 6. And he might also think it means 6. So if we do that on average, we're each going to be off by 6, and if you square 6, you get 36. If we both said 6, we have no diversity. And so as a crowd, we're off by 6, or 36, right? But suppose that I think it's 6, and Cooper thinks it's 18. I have an error of 6, he has an error of 6, but our errors go in different ways, so we also have a diversity of 36, right? Because our average guess is 12. He's 6 above, I'm 6 below. So in this case, our crowd error is 0. So if we make the same errors, we don't get any benefit from diversity. If we make different errors, we get this big benefit from diversity. Okay, so let's play this for fun. So this is the Saturn V rocket. And what I need is this to work. I'm going straight to Khan Academy now. All right, so I need 5 people to, let's go, you 5 right here. Think of what you think the height of the Saturn V rocket is, okay, in feet. Get a picture that I just took away. So rough guess. What? 1,200.
2,400.
Feet high, okay. Saturn V rocket. 1,000, okay. 1,100. 1,200, okay. So we've got, the actual height is 363 feet high, okay? So let's try something simpler. Let's go with this 5. No, so, by the way, they did much better. My students had 50,000 feet. I'm like, really? Yeah.
One of the problems is I heard what their answers were.
No, that's right. So one reason why, that's why I said think of your answer and don't. So one reason this is an interesting thing to do is if you hear what other people say, you tend to bandwagon. This is what Keynes called sort of the Keynesian beauty contest. Right? So if you think, so once you said 1,200, if you'd have said 200, we'd have had a bunch of guesses of 200. Okay, so this one we're going to include you again, so just ignore them. So think of it, even like write it down in your head. This time you're going to guess my weight. Okay, so hopefully we won't be off by a factor of 5. All right, so.
175.
170.
160.
170.
Oh,
160.
oh my goodness.
180.
Holy cow, okay. I weigh 193 pounds. I'm about 26. It's a BMI. Okay, so let's, so 160, what was the next one? 170? 175, 180, and what was the? 2 160s, okay. So what you can see then here is you can see the guess, let's see if I can get this down. So what you can see is you can see the error of each person in these red bars, and then you can see the average error, the crowd error, and the diversity. So what you see here in this particular case, there was very little diversity. So the average error is approximately the same as the crowd error, but the crowd error is still small, right? So if we changed one person, let's just change one of these 160s to 220, right? So increase the diversity. Now what you see is, you've got those errors of the guesses. The average error is still big, but the diversity is larger, and the crowd error is smaller. Now the point of this is an algebraic identity, so it's always going to be true, right? Crowd error equals average error minus diversity. What's interesting is I teach this online course that's now had like 500,000 people take it. I'll get emails from people saying, literally they'll say this, Scott, I hope you're sitting down, but I just took data from like a jelly bean guessing contest or something we did, or even like predictions within our firm, and I plugged it into this formula, and it works. Crowd error equals average error minus diversity. So I send them back this little slide that has like a right triangle on it, where one side is 5, one side is 12, and one side is 13. And then I say, hope you're sitting down. Check this out. 5 squared equals 12 squared plus 13 squared. The Pythagorean theorem works again, right? The point is, and this is the point of using these models in the social sciences, the models are always right? They're logically consistent. So when I put the picture of Carl Simon up earlier, right? One of the reasons we do these models is to make sure we get the logic right. The challenge within the social system is how do we create incentives, how do we do things, how do we construct institutions so that we generate diversity in how people think about things. And so that's why, again, the point of this is the value of having many different models, because the many models are likely to give you some diversity. I'm going to leave page. Let's go back to, okay. So let me push this a tiny bit deeper to show you how the diverse models work. So what we can think of when we construct a model is a model consists of, in some sense, nouns and verbs. And the nouns are categories. So what you can do is you can think about partitioning this set of things out there into categories, because you simplify. And then within each category, you're making a prediction. So suppose I've got 4 houses here, and these are the values of their houses. And the natural way to put these in categories is to say the ones with the windows and the ones without the windows. Now, whenever you look at data like this, you first have to say how much variation is there in the data. And the total variation of the data is 100,000. So, right? So I can think of this as a big box. Here's how much variation I've got to explain in the world. So what I do is I create categories. One category is the houses without windows. The other category is the houses with windows. Once I construct the categories, I've made an error. This is the all models are wrong. Once I divide things into categories, I've necessarily made errors, and I can compute what I call the categorization loss, which is if I made the perfect prediction within each category, how badly would I do, right? And what you get is the categorization loss is 10,000. So if I could predict perfectly, I'd explain 90,000 of that variation, and I get 10,000 wrong. It's just the cost of using the model, the cost of the simplification. But the problem is once I have a model, I'm probably not going to make the perfect prediction. Right? Even once I put it in categories, I'm still going to make some mistakes because my model will be wrong. In some sense, the verbs will be wrong even once I've created the nouns. So there's going to be some sort of prediction error. So what I can think of then is whenever I construct a model is it's wrong not once but twice. Once it's just wrong by virtue of being a simplification. This is George Box. All models are wrong. There's a category loss. Then there's a prediction error, and that is that like we never have perfect control over a model. We don't have enough data. We make there's just it's not going to be exactly right even once we've created the right words. And then whatever we haven't kind of screwed up by making the model itself or predicting with the model is what we explain. So in this case, we'd explained 80,000 of the variance. So now I can write something that I call the categorization prediction theorem, which says the variation, total variation in the system consists of three things: that which we can explain, that which we lose from the model, and that what we lose from the model sort of being wrong. Now what follows from this then is if I have many different categories, they're going to have different categorization laws, right? And so by the diversity prediction theorem logic, they're going to be better than any one model because they make different errors, okay? So let's play this out. This is Giancarlo Abecasas, who's here at Michigan, brilliant guy, National Academy of Science, does fabulous stuff in bioinformatics. I'm putting this slide up because there were three groups that were funded by an agency to identify genes. There's a green line, which is the Eli Broad Institute at Michigan State. There's a red line, which is Harvard, and there's a blue line, which is the University of Michigan. Lower lines are better. That's why this slide is up there. And what you see is that Michigan and Harvard are pretty close, and Michigan State's a little bit trying harder. So what you get here, though, which is interesting, is so they are presenting the results, and this is sort of like, how many mistakes they're making identifying the genes. The person who funded this said to them, I gave a talk on diverse models, and Giancarlo was after me, and he goes, this is so unbelievable that you're just giving this talk, because we have these three different models, and our funder said, why don't you have the three models vote? You've got three different models, they're different, why don't you just have the three models vote? The dark blue line that's better than any of the three models is the three models voting. Right? So we can talk about like guessing the weight of steer. We can also talk about like really sophisticated, like the most sophisticated attempts to identify genes. Three models are better than one, provided the models are different. Okay? But genetics, genes, cancer, living forever. Let's talk about something important, movies. Okay, so 2006, Netflix, Reed Hastings, the CEO of Netflix, decides, I've heard about all this stuff of crowdsourcing, groups of people solving problems. Let's do this for fun. I'm going to take all of my data about movies and put it on the web, and I'm going to let people see if they can be better than we are predicting which movies people like. And if anybody can beat us by 10%, we'll give them $1 million. Not bad. Now the way this works, here's what they had to do. So the way this works, if I go onto Netflix and I type in Avatar, it'll predict 5 stars for me. That's because I have 2 teenage boys, and that's the kind of thing they like. They figured out our preferences, and so they'll predict 5 stars. Right? If Patrick Shields is over here, who's an intellectual, bright guy who only watches like dark Swedish films, right? They'll probably give it 1 star. This is sort of beneath him culturally. If either one of us types in Rush Hour 3, or any of you, 1 star. Horrible movie. Okay? So the thing is, so there's some movies that are like really easy to predict, like Rush Hour 3. There's other movies that are hard to predict, like Avatar, because you're predicting for each person. Okay? So the way this works, there's 6 years of data, 500,000 users, 18,000 movies. They divide this into the standard sort of a training set and a testing set so you don't overfit, and everything works fine. And again, you got to beat them by 10%. All the models, remember I had this sort of categories of houses? All the models had the same flavor. And by the way, who's playing? All the big boys and girls. So all the like data miners, data scientists from leading corporations and universities are playing in this, and they all have the same sort of models. Each movie gets represented by a vector. So these little things like P1, P2. P1 might be, is it an action movie? P2 might be, is there a car chase? P3 might be, how much money did it make at the box office? P4 might be, how many weeks has it been on video? Right? So these are properties of the movie. One of the properties of some of the movies in some people's models were, is Morgan Freeman or Will Smith in the movie? Because it turns out they're in no bad movies. Okay? Each person then gets represented by a vector. So if you liked car chases, that gets a positive thing. If you don't like it, it gets a negative thing. And the question is then just sort of like, you're trying to fit each person and each movie. So who wins? Well, so the leader in this is this guy, Robert Bell, who's on the left. His team at Bell Labs, ironically. He was working at Bell Corps. And their best model could beat it by 6.8%. Not bad, but you need 10% for $1 million. But here's the funny thing. They had a lot of models. They had 107 models, in fact. So when they combined their 107 models, and they created their like sort of democracy of models, they got to 8.4%. How come? Well, we could just use the diversity prediction theorem logic, right? Crowd error equals average error minus diversity. If you've got 107 different models that are different, right, they're going to be better than any one of them. So they get to 8.4%, and they're hanging out at 8, 9%, and it's been 2 years. And at one point, Dr. Bell, he gave this wonderful talk here at Michigan a couple years back. His boss comes into him and pretty much has to genuflect, right? Because this guy's beating everyone. And says, it's great that you're winning, but you have this thing that we call here a job. And it'd probably be great if you went back to your job. And so Dr. Bell basically said, okay, fine, he cues the Rocky music, right? And he says, you know what? I'll just end this thing now. And his boss is totally perplexed because he's been doing this for 2 years and he's not at 10%, and now he's going to get to 10%. So he says, how are you going to do this? And he says, easy, I'm just going to call someone dumber than me. His boss says, who would that be? He says, anybody. Right? No, I mean, like, he's the best, right? This is the man. It's been decided. We got 2 years of data. We know who's the best. He's the best. There's no disputing that. But what he knows is all he's got to do is bring in people different than him. So he brings in the team in second place. They don't bring in the team in third and fourth place because they're actually, even though they're smart, they're not that different from the team in second place. And they bring in the team in fifth place. And then they get, when they combine these models in this combined team, Belcor's pragmatic chaos, to 10.1%. Now, one of the big breakthroughs in the combined models is one of the teams had figured out a way to determine sort of multiple personalities within a household better than the other teams. So let's go back to Patrick. He's only renting these like dark Swedish films, and he rents Blue's Clues. And you're thinking like, and so most of the models would be like, oops, he misinterpreted the word blue or something, right? But instead, the Canadian team in this group figured out that maybe he had a kid, maybe he had a grandchild, right? So they could figure out that there's, these transitional life changes better than other people, and that was one of the things that gave them the big bump to get about 10%. So they win. They win the $1 million. Everything's fine, except for they don't. The rules say you've got 30. Once somebody gets to 10%, the contest ends in 30 days. The reason why, they were concerned, there's a bunch of schools, they tend to be public schools like Illinois, Michigan State, where undergraduates have access to the supercomputing clusters for a certain amount of time. Reed Hastings was concerned that like some undergraduate might download it and hit the return key. So you don't want to give $1 million to some undergrad who like scrape, return, thank you, right? So he said, okay, at least let's make this thing last 30 days. Now it turned out someone using the Beckman Institute's computers beat it by 5% within about 4 days, I think. So if he'd have said 5%, he'd have been right. But now this looks kind of stupid because it's been 2 years and somebody finally got over it. Now they got to wait another 30 days, and this money's going to go to New Jersey public schools, so this seems silly. Now, Dr. Bell tells this amazing story about this. Their reaction at this point, I actually can't say in polite company. Not because they really cared that much about 30 days, but because they knew two things. They knew they were smarter than everybody else, and they knew the other people were more different. They knew there were 23 other teams from 30 countries who they had been beating for 2.5 years. And they knew they were smarter than them, but they knew these other people were more different. They knew, for example, that like the Swedes have words for standing alone in the forest at night. And the Swedes have a word for like standing on your front porch waiting for your guests to arrive who are late. Stuff like that, right? And that they might have coded movies in that way. And that all these other people who previously only had an incentive to win and now only have an incentive to combine their models and really leverage their diversity are now competing against them. So it's now the good against the diverse. And with 2 days to go, the diverse win. And then the good win. And then the diverse win. It comes back and forth, and it ends up, these are the root mean squared errors. This is the error terms. Belcor beats them on the 5th decimal point. But the ensemble was so diverse, they even had someone who read the rules, and the rules say 4 decimal points. So it's a tie. But then it goes, who submitted first, and Belcor beat them by 22 minutes. So Belcor gets the money, which is great. Okay, so we've seen the diversity prediction theorem, the logic of diverse models 3 times. We saw it within Belcor. 1 model, 6.8, 107 models, 8.4. We see it when they combine, second time when they combine with these other teams not as good as them to get to 10%. We see it a third time with all these also-rans, and when you read the New York Times report or the Slate report of this, what the ensemble says is, we knew we'd be better. We just can't believe how much better we are. Right? I mean, they knew that they could get from 8, when they combined their models, they're all sitting like 8%, they'd get better, but they couldn't believe they got to 10%. Now, 8 to 10% may not seem too much to you, but think of it in terms of like investing your money. Somebody could promise you 10%, not Bertie Madoff, but someone else could offer you 10% versus 8%, you take it. So this is a big increase. Okay, now so this is sort of how it ends. They're both at 10.06%. And the beauty of this is the ensemble team has a lot of grad students on it. And so when it ends, they basically say, here's the final results. It's unequivocal. Belcore takes second place. And they're absolutely right. How come? What's better? What? Well, so I've got one that's 10.06, another that's 10.06. What has to be better? These are two different models. What has to be better?
The one with more models?
Combine them. Right. Belcore does take second place. Right? So I was visiting a large company one time that invests high-profile clients on whether they're going to get investigated, would be the word, I guess, by the IRS. And they had software that predicted this, and they had new software. And the new software was only a little bit better than the old software, but they basically used the same technique. And the CEO said to me, he goes, wait, are you saying that rather than use our new software, we'd probably do better by averaging our new software with our old software? And his chief statistician, she raises her hand, she goes, no, he's not saying that. The CEO's got him totally confused, and she said, no, he's not saying probably. Right? If you have two models that are equally good and they're different, 5, 12, 13, it's got to be better. The average has got to be better. It's just it's a mathematical fact, right? So when you think about prediction, diversity of models is ability of models. Okay? All right. So this gets to sort of the last point, which is this notion of sort of foxes but hedgehogs. So when you think about the problems we face, and I'm just going to do two, but I could do a list of them, things like climate change, inequality, obesity, international relations, developing a safe power grid, alternative energies, all sorts of incredibly hard, complex problems. What we need is lots of models. So let's talk about climate change really quickly, right? So there's average global temperature graphs, right, that show things going up. There's a ton of models. So one model that we use that we teach middle schoolers is just sort of the pot of water model. We think of the Earth as a giant pot of water, right, and it's heating up, and stuff is going out, and you can basically say as there's more carbon in the atmosphere, it heats up more. There's fancy carbon cycle models as well that take into account every unit of carbon, and you talk about how much is going in and how much is going out, and you try and account for all of it and show how that then relates back to the pot of water model. There's also, within sort of my tribe, the economist, there's something called the DICE model, which is the Dynamic Integrated Climate Economy model. And this has, in addition to things like the gray things, like atmosphere, land biota, soil, surf ocean, deep ocean, fossil fuels, that sort of stuff, it has capital markets and productivity and throws in economic growth. Right? So it links an economic model with a climate model that's not quite this sophisticated, but it's more sophisticated than the pot of water. Okay? Because the models have to be simple. Now there's something called the IPCC, which runs models on what's going to happen to the climate. And what you see is the black line is what you hear about in the press is the IPCC model. What you're seeing in the other lines is actually the IPCC models. So they don't use one model because they know that would be wrong. It wouldn't be wrong because they know all models are wrong. Any model is going to be wrong. What they use lots of models, and they use what they call sort of ensembles of models, and then you average across those ensembles and say this is what you think is going to happen. So do they know what's going to, so this is in some sense a sort of error thing, right? So temperatures it's true, temperatures might not go up by much, but they might go up by a lot, right? So when you see percentages like this, what we know from the models is that we don't know, but we also know some sense of range, okay? So let's look at inequalities. This is more my space. So if you look at household wealth, right, you see that 74% of the wealth in the last 30 years has gone to the top 5%. So wealth is really accrued to the rich. If you look at income, average income in the United States, that's also gone to the wealthy. But one sort of mitigating thing here is the wealthy now are different than the wealthy were in the past. It's different people, so it's not quite as bleak as this looks. Why? Again, there's lots of models. Famous model recently by Tom Piketty. This is super complicated, so here it goes. Piketty's model is this: R is bigger than G. R is the rate of return on capital, G is the growth rate. In a standard, what we call solo growth model in economics, this is always true. The rate of return on capital is going to be higher than the growth rate. That means, let's think of it this way, suppose capital grows at 10% and the economy grows at 5%. If you're rich and you just keep your money in the bank, it's growing at 10%. The economy's growing at 5%, so guess what happens? You just get richer and richer and richer. So there's something we use, a simple model I use in my class called the rule of 72, which is take your rate and divide it into 72, and that's how long it takes to double. So 10% will double every 7 years. So that means in 14 years, your money's gone up fourfold, right? In 21 years, your money's gone up eightfold. So as long as R is bigger than G, the wealthy are going to stay wealthy. Now, people have criticized this because it's too simple, and so they've gotten super complicated. And this is sort of Brad D. Long's version of it. So it's actually R minus T minus S, because we actually tax people, so you don't get the full return, you get it taxed. And believe it or not, you spend money as well, right? Now, some people, one of my friends jokes is S stands for both spending and stupidity, right? So you might invest in dumb stuff, and if you do that, that's going to return that, but the growth rate of the economy is going to be the growth rate of the economy. So whether or not this explains it or not, at least it gives us some sort of framework explaining why we might see wealth inequality. Now, Joe Stiglitz has a completely different view. Stiglitz's view is that there's been sort of increased monopolization, right, and the rich are getting a larger share. So Claudia Golden has a book on this and sort of the race between technology and capital as well. And what you see is if you look at the increasing gap between productivity and wages, the blue line is productivity, the green line is wages. So workers are getting more and more productive, but they're actually, because they're more productive, you need fewer of them, which means there's excess workers, which means therefore they don't have much power in the market, so they actually get less money. Okay, so that's Stiglitz's story. And it's true. Piketty's story, to some extent, it's true, but it's also wrong. Stiglitz's model's true, but it's also wrong. There's also a set of books called The Winner Take All Society and something called Positive Linking by Paul Omerod that basically argue that now there's all these sort of weightless goods, and there's also, we have all this information, we can sort of go to the best thing. So one of the jokes that economists will make is no one goes into a restaurant and says, give me your second best steak, except for an economist, right? And the reason why is because the first one might be overpriced. But the point is, now there's so much information that what you get is instead of getting sort of nice bell curves, right, that we'd expect from a random distribution, we get the things that we call power law distributions, where you get these incredibly long tails. So there's big winners, right? So Peter Thiel has this new book out called The 0-1 Society, where he basically says, look, the very best person just makes a lot more money than the second best person, whereas in the past that didn't seem to be true because markets weren't as connected. So again, this is also to some extent true. It's giving us one lens, a different categorization, explaining some of the inequality, right, as are the other ones. Last one, and this will be sort of fun, is there's an argument of what we call assortative mating. So it used to be the light blue lines are 1960. So this is the percentage of people who married people with the same level of education. So if you had a graduate degree, the odds that you married someone with the same level of education in 1960 was 10%. Now it's 40%. And if you had a college degree, it was 25%, and now it's 45%. Okay? So it used to be, if you're an incredibly smart person, you'd just marry someone beautiful, right? But now, and this, I'm putting up Yuji, my friend, right, who's does work on assortative mating. Now, someone bright like Anjali isn't going to go for the, eye candy, right? She's going to marry someone smart like her, someone who studies assortative mating, right? And that's going to lead, and the argument this leads to inequality because what you've got two high human capital parents who then pass that on to their children. Okay, is there evidence for this? Yes. Does it affect inequality? Yes. Again, it's one of these many models we use to try and understand the phenomenon. Do we know that this works? Do we know that many models work? Do we know that it makes you a better thinker? The answer is yes. So in one of the most important books in social science in the last 10 or 15 years, it's by Phil Tetlock, and it's called Expert Political Judgment. And this is kind of a jokey title, because what he does is he analyzed 28,000 predictions by 284 people over the course of a decade. So he's one of these rare people that after he got tenure, he decided, I'm going to take on a huge project that's not going to yield any dividends for a long time. So he studied predictions of all sorts of people, experts, right, non-experts, Congress people, media people, everybody can imagine. Now, what he shows in this is that there's two types of people. There's foxes, who are many model thinkers. These are people who think of things in lots of different ways. And there's hedgehogs, who are people who have one model. Now, what he shows is the people who have one model, the people who say markets work, they're worse than random. So if you listen to Rush Limbaugh or if you listen to Al Franken, you're better off doing this. Take a distribution of all the things that can happen, divide it into three parts. It could decrease, it could be the same, or it could increase. So these are equally likely to happen based on past data. Then randomly pick. You're better doing that than listening to someone who's an ideologue, according to Tetlock's data, again, with only 28,000 predictions. So this is a huge data set. So the other thing that comes out of this is models are better than people, way better than people. So, oops, this slide's out of wing. So here's Here's his graph. On the x-axis, the horizontal axis here is how calibrated you are, so how accurate you are. And the y-axis is how fine of predictions you make. Now, what you see here is there's this one thing that's way above anything else. All these other things are people. Those are formal models. So formal models are way, way better than people predicting. But the interesting thing is models plus people are better than people. So this is long-term capital management. I've got a star there for no pun intended here, right? So this was a firm that had a bunch of Nobel Prize winners in it. And if you remember, in the 1980s, they nearly caused the entire world financial market to collapse. And because they were betting on something, their model said these two rates should line up, and they didn't, right? So they had the model, but they didn't sort of combine the model with their own judgment, right? So one of the things that comes out of this sort of things as well is people plus models are far better than models, right? So the idea here, when you confront this, sort of incredibly complex world, is what you want to do is you want to develop models. And once you have a model, whether it's in so when you have an assortative mating model, when you have these sort of network models, when you have these, Piketty sort of investment models, once you have a model, you can apply it in lots and lots of cases. Once you have a problem, what you don't want to do is just have one way of thinking about it. You want to have multiple ways of thinking about it. Because, again, in the predictive context, crowd error equals average error minus diversity. The same is true of models. The crowd of models is equal to the average error of the models minus the diversity of models. So what you want is you want to have lots of different models to look at things. And if you do that, right, you're just going to make better predictions, you're going to design things better, you're going to understand things better, but you're also going to recognize that the social world we live in, because it's so complex, we're not going to be as good as the physicists. That's just how it's going to be. We may be better looking, we may be more fun, right? But we're not going to be able to predict as well as they do. All right, thank you very, very much.